Well, here we are again. It looks like this is the way it's going to go. You might as well try and get comfortable. That's what I'm trying to do. So, continuing with chapter 16, I don't know that we're going to be able to do this in one video, so I'll probably break the tail end of this into two, but I'll load them up tonight. So, here we go. Chapter 16, acid strength. And taking a look at acid strength, what we want to do is we want to look at the acidity and basicity of salt solutions. Now, just to remind you, this is the salt that you're probably most familiar with, sodium chloride. But a salt is really just an ionic compound, which is potentially the result of an acid-base reaction. So, this particular salt, it dissociates completely into Na plus aqueous plus chloride ion aqueous. And the question is, are salt solutions acidic? Are they acidic in solution? That is, do they produce a bunch of hydrogen ions? Are they basic? Do they produce some number of hydroxide ions? Or are they neutral? Do they not affect the acidity of the solution at all? And that's what we're going to study in this last section. And I might mention that this section is something that students have a lot of problems with. It's very conceptual, so here we go. Okay, in studying the acidity, basicity, or neutrality of salt solutions, I want to remind you of this relationship between Ka and Kb. So if Ka is the equilibrium constant that we use for an acid, it's called the acid dissociation constant. Kb is the equilibrium constant in this context for its conjugate base. And then you remember Kw, that is simply the equilibrium constant for the autoionization of water. And we discovered this relationship that the larger the equilibrium constant for an acid, that is, the more product favored that acid is, the higher the hydrogen ion concentration, the dissociation or ionization of that acid is, the lower the Kb for its conjugate base. And then Kw is the equilibrium constant for water. And if we're at 25 degrees, that's going to be 1 times 10 to the minus 14. And then we also discovered that if we take the negative log of both sides of this equation, what we wind up with is pKa, that is the negative log of the Ka, plus the negative log of the Kb, which is equal to the pKw, which at 25 degrees is 14. So what I want to remind you of is that there is this inversely proportional relationship between the equilibrium constant of an acid and the equilibrium constant of the conjugate base, okay, or the base and the conjugate acid. So let's take a look at this guy right here. So this is a salt. It's called ammonium chloride. And so when I put ammonium chloride in water, it is a completely soluble, strong electrolyte. So we're just going to drop it in some water. It will dissociate into NH4 plus chloride ion. And these two will be in aqueous solution. All right, so let's examine the chloride ion first. Well, the chloride ion, if I added a proton to this chloride ion, so if I just added H plus to that, what I would get is HCl. Well, HCl is a strong acid. It is a strong acid, it's a strong electrolyte, it dissociates completely. And remember, the Ka-Kb relationship. with respect to Kw. The bigger the Ka, that is, the stronger the acid, the weaker its conjugate base. So since the conjugate acid of chloride ion is HCl, that means that the Kb for chloride ion is going to be neutral. So chloride ion is not going to affect the pH of the solution. It will be completely neutral. We don't need to worry about it. On the other hand, let's take a look at NH4+. NH4+ is the conjugate acid of ammonia. So it will actually, in solution, dissociate a proton, give the conjugate base of ammonia. Ammonia is a weak base, therefore the ammonium ion is a weak acid. And as a weak acid, when ammonium ion dissociates that proton, the pH is going to go down because the hydrogen ion concentration goes up. So ammonium chloride, when it dissociates, gives us a neutral anion, and it gives us an acidic cation. And this salt, ammonium chloride, will be acidic because of the ammonium cation. You really want to keep your eye out for the ammonium cation. It's always acidic. Weakly acidic, but acidic nonetheless. Okay, let's take a look at sodium acetate. And here's sodium acetate. It is a completely soluble salt. So if we dissociate it, if we throw it in water, NaC2H3O2, throw it in some good old H2O, it completely dissociates into the sodium cation and C2H3O2. Now, let's just take a look at the sodium cation first. Anytime you see a cation floating around in water, what you're asking is it acidic? Well, think about alkali metal cations. Alkali metal cations are always spectator ions in any of the metathesis reactions you did in Chem 1. They are unreactive. They're perfectly happy. They have noble gas electron configuration. So it's not going to affect the acidity of the solution at all. But look at acetate. So acetate is, let's write it out here, O2 minus. If I were to add a proton to acetate, I would have HC2H3O2. And this is the conjugate acid of acetate, which is the conjugate base of acetic acid. This is a weak acid, and acetate, as it turns out, is also a weak base. This is one of the things that you're going to notice. Look at the Ka times Kb relationship. Okay? The stronger the acid, the weaker the base. Well, acetic acid is a weak acid, which means that its conjugate base is a weak base. So if I put C2H3O2 acetate in water, and how did I do that? I simply added sodium acetate to water. It completely dissociated. What it's going to do is behave as a weak base, like ammonia behaved as a weak base. It's going to accept a proton from water, make HC2H3O2, and every time it takes a proton from water, what does it leave behind? It leaves hydroxide, and the hydroxide in excess makes this a basic solution. So sodium acetate, guys, this is a basic salt. All you're looking for to tell whether the salt is basic or acidic is primarily look at the anion first, because most of these guys are going to be basic. It'll be basic or neutral. Some of them will be acidic. You're going to really look for the ammonium cation, that NH4 cation for acidic salts. Basic salts just look for the conjugate base of weak acids. Let's take a look real quick at sodium nitrate. This is sodium nitrate. The first thing you do when you're trying to sort this out is dissociate it. Put it in water, because that's how it's going to be, either acidic, basic, or neutral. Now, let's do the anion first. If I added H plus to the anion, what would that give me? It would give me HNO3, and this is nitric acid. Nitric acid, you need to know your strong acids, and it is a strong acid, which means that nitrate is neutral. Its Kb is so small that we can ignore it. And here again, we have an alkali metal cation, which has a really tiny, tiny Ka. It's a spectator ion. It doesn't do chemistry in solution, and so we'll just call it neutral as well. So sodium nitrate, this is a neutral salt. This is completely neutral. It's like sodium chloride, or any alkali metal nitrate, or any alkali metal chloride. So when you're trying to decide whether or not a salt is acidic or basic, look at the cation. And guys, if the cation is ammonium, it's almost always going to be acidic. I'll show you when it might not be acidic when the cation is ammonium. So ammonium chloride contains the conjugate acid of the weak base. The weak base that they're talking about is NH3, ammonia. This is the conjugate base of the ammonium cation. This is a weak base, which means that the ammonium ion is a weak acid. Weak acids and bases have weak conjugates. So ammonium chloride is going to be an acidic solution. Alkali metal and alkaline earth metals, group 1 and 2, don't affect the pH. So if you see something like potassium as the cation on the salt, like potassium acetate, C2H3O2. This is actually a basic salt, because when it dissociates, potassium ion will not affect the pH, but the acetate, C2H3O2 minus, this is the conjugate base of acetic acid, and so this will give you a basic solution through base hydrolysis. Okay, so ignore group 1 and group 2 cations. They're always going to be neutral. All right, anions might be basic. You're looking for the conjugate base of a weak acid if you're looking for a basic anion. So as we've said, sodium acetate is basic because it dissociates in water into sodium cation, which we don't care about. It's neutral, plus acetate, C2H3O2 minus, and it does it through this reaction. A proton is accepted from water by acetate to form acetic acid, the conjugate acid of the acetate. So if its conjugate is a weak acid, then this is going to be a weak base, the anion is. Okay, the conjugate bases of strong acids are always neutral. So your strong acids like HCl, chloride is neutral, HNO3, nitrate is neutral, HClO3, chlorate is neutral, H2SO4. So when this dissociates, remember this is polyprotic, only the first proton is acidic. Here is the conjugate base of the strong acid. This is sulfuric acid, and so you won't have to worry about sulfuric acid because it's the conjugate base of a strong acid, and so it's either neutral or perhaps even slightly acidic itself, but we'll just say neutral. Ooh, neutral. Okay? So the conjugate base of a strong acid is a neutral base. It's not basic at all. For a given salt, examine the cation. Is it capable of donating H+? If that's the truth, then it might be an acidic cation. And the big one that you're going to worry about in this case is ammonium ion. Examine the anion. Is it the conjugate base of a weak acid? If the answer to that is yes, it's probably basic. Okay, and so let's take a look at NaNO2. This is sodium nitrite. Dissociate it. Na+. And then you have nitrite anion. Well, the Na+ is an alkali metal cation. We're not going to worry about it. It's neutral. But nitrite, if I added a proton to nitrite, that would give me HNO2. Not HNO3, but HNO2. This is nitrous acid, and nitrous acid is a weak acid. And since this is a weak acid, then its conjugate base, nitrite anion, is a weak base. If the cation is acidic and the anion is basic, both Kb and Ka and Kb have to be considered. So one of the classic examples of this is NH4HCO3. This is ammonium bicarbonate. It's a soluble salt. It's going to dissociate into NH4 plus HCO3 minus. You would look at the Ka for the ammonium ion and the Kb for the bicarbonate anion. Whichever one of these is largest is probably going to dictate whether this is an acidic salt. If Ka were larger, it would be acidic. If Kb were larger, it would be basic.